So, yeah, good morning to all your first years, and to you guys who just showed up so you can tease me about it later. When Stacey asked me last week to just give you... Let me get this on first. When Stacey asked me last week to just give you guys a bit of an overview of my research, I was quite keen when it all started, until I had to get the slides together, and I realized that I might not be able to make this as exciting as Stacey made robotics look. I think even in first year you could have a look at a YouTube video and pretty quickly build a little robot that can follow a line, and it's kind of cool to show your friends, and it's not the biggest stretch to see. I mean, obviously you have to work a lot to get there, but to like where Stacey and them are in building robots that can run as fast as human beings, for example. What doesn't really make for that great conversation with friends would be something like discussing how your phone, with its small battery and small antennas, really low power device, is capable of communicating with a cell phone tower that's several kilometers away. Being able to send information across, and at that small amount of power, so that your battery lasts longer than a few minutes. But it is quite impressive, and you'll probably get more of appreciation for it as you get further on in UCT later years. You do a bit more signal processing, and you'll get an appreciation for that kind of stuff. So I'm going to try and make this sound as interesting as I can. So most of you know me by now. I haven't been in lectures much, but I'm a master's student here at UCT in radar and electronic defense. My research is co-supervised by SANSA and UCT. I'm part of the UCT radar and remote sensing group that's located here on 7th floor. So, yeah, and I'm your TA for the course, for those of you who came late. So in these slides, I'm just going to basically try and show you all the high school concepts that actually prepared you to even study something like radar. Things you probably didn't even know was preparing you for it, but we'll just go through that, show you a bit of that. And then I'll just show you the kind of things that kind of branch into radar after that, things you'll learn in your first few years here about electric fields and, for example, the radar range equation. Probably not in your first few years, but... and then I'll try and make it a bit more interesting by showing you a few of the radar design concepts, just what's involved in designing a radar. And then just to complete the picture, I'll show you what I did in my fourth year as my fourth year project. So what you'd be able to do after 4 years. And then at the end, I'll just show you a bit of my master's project, just a very, very broad overview of that. Right, so back to high school. Stacey's drawn this on the board a few times, I think. That's probably fairly common. Electric field, around 2 charges. You would have learned in high school that if 2 positive charges, you've got electric fields that repel each other. Or like charges, opposite charges, you get an electric field that looks like this. And some of the questions that I'm not sure if you actually came across in high school would be, how far does this field go? Something to think about. How fast does it go? Is it instant? If I had nothing there and I suddenly made a positive charge and a negative charge appear out of nowhere, is that field instantly there? Answer is no. The answer to the 2 questions is, the field goes infinitely into space. If I make a call on my cell phone, that signal that my cell phone sends will go all the way into infinity, into the end of the galaxy. The power of it decreases very quickly, which we'll see in later slides. But the point is that this electric field, and it's never that simple. I mean, every single charge in the universe has an electric field, and they're all combining to make an interesting combination of fields. And then the other thing is that when those 2 charges would just appear out of nowhere, how quickly does that field set up? How long will it take to, say, sense that field a few kilometers away? The speed at which that, what we consider a wave, travels is 3 times 10 to the power of 8 meters a second, speed of light. The second picture up here, you'd also seen from high school, is the Doppler effect. If a siren, these are our sound waves, if a car drives towards you, you hear a higher frequency. As the car drives past you and away from you, you hear a lower frequency. That's also integral to radar. So here's just an animation of how, now we had the 2 point charges before. This is now an antenna. So here we just have a dipole antenna. And all that's happening is one side of the antenna is more positively charged than the negative side than the other side, and we just oscillate between the two. And those oscillations create an oscillation in the field around it, and you can kind of see how it propagates outwards. This is the most simple kind of antenna. There are much more complex antennas that I'll show you a bit later, but that's just an illustration to show you how the field would set up. How can you use this? Well, that's what radar is all about. Can you sense this field at a certain distance? What happens if it hits an object? Does the field bounce back? How much of that can we actually measure? So now it gets a bit hectic. Here's the radar range equation, which is basically what you spend your first year masters just learning about. And the symbols here, S is your received power, P is your transmitted power. This whole equation here has to do with your antenna and the wavelength and the reflectivity of your object, blah, blah, blah. But what I want you to look at is this term over here, 1 over r to the 4. You can imagine that when r gets bigger, r to the 4 becomes a really, really big number very quickly. And that means 1 over r to the 4 becomes a very small number. It's a really small factor of your transmitted power that you receive in terms of distance. Sorry, r is your range away from your target, wherever your target is bouncing back from. So, for example, here you have an antenna. It's transmitting a signal. This is a pulsed radar. Transmits the signal, hits a target. That signal scatters in all directions. It's reflected off that target. Oh, and by the way, this is not examinable, so you guys can just chill and be a bit hectic to test you on this. But some of that signal comes back, and basically that'll tell you how much power comes back. It's a very, very small amount. Just to give you a basic idea, if a plane is flying at 20 kilometers from the airport, and you have an antenna trying to pick up that plane, this is the factor by which that power will decrease. You get a very, very small signal back. And the electronics involved in building a system like this, that can transmit a really high power out and then listen to a really, really, really small signal is quite complicated. And that's kind of that's why radar is such a specialized field, really, is being able to work with those electronics, I guess. Here you have a Doppler radar. That's just sending out a signal. As the plane comes past, that signal is increasing in frequency. As you can see, the signal that goes back to the antenna is a higher frequency, closer spaced pulses. And that's how we can, for example, tell how quick a plane is moving. So just on the design of a radar, it's very broad overview of it all. There you have a missile. Often missiles have their own radars on them that can actively track a target. So that missile will change its course based on what that radar reading is giving it, and it can hone in on a specific target. Kind of in parallel with radar, you get telecoms, which would probably be more involving phones and how that signal propagates. All of these sketches kind of show you where that transmitted power from the radar goes. This is quite an interesting thing. This is what's called a phased array, where each of these little dots here is an antenna by itself. And all it does is every antenna maybe propagates a signal a bit later or a bit earlier than the other one. And what happens with superposition is some of those signals would cancel out in certain directions. But in certain directions, those signals will overlap perfectly, and you get a really strong echo. And you can basically steer this antenna, this beam, in any direction you want without having to manually steer the whole antenna. This is quite new technology, and there's a lot of research going on in that right now. Well, to actually be able to create the signal, and then, like I told you before, to be able to listen to a really small signal coming back, there's a lot of electronics involved. You need to first take your small signal, amplify it up, make it really powerful. Amplification is something you'll be doing in the labs, probably at the end of your labs. But taking a small signal, making it really big, making it really powerful before you transmit it, and then making it big again once you've received it, a really small signal, to amplify it, make it a bit bigger, cancel out all those other nonsense frequencies you don't want to see. That's what's involved here. Not really necessary to go into details about that. After that, once you've received all these signals, now you kind of have to make sense of what you've received. So it's just really broad. Don't worry too much about this if you don't understand. But like, here's a chirp. That's the signal we've transmitted. After a little bit of time, so this is time on the x-axis, you'll receive a little echo back from a target. So that's an echo from a target. Here, two other targets, fairly closely spaced, a bit further away, have also returned two echoes. And you can see some of it overlaps there. I mean, if you know what you're talking about, you could tell this is two targets. This isn't great, though. A radar like this wouldn't be very useful. The fact is, this is not actually what you'd receive. What you'd receive would look more like this. There's a lot of other frequencies, there's a lot of noise. And you really can't make out what signal is here. So just to give you an appreciation of the signal processing involved in radar, what we have certain algorithms, correlation functions, where we go and look for this signal in this bunch of noise. And you run that function, which I'm not going to go through, obviously, but you run that function, you run it through here, and what you get out is a very narrow little lobe peak where you can pretty much quite easily say the target's very close. The echo came back at that time, and at that time. And it's nothing like this where it was completely ambiguous. So just to show you what kind of signal processing is also involved. I guess you'd probably do this more in like ECE. Just for interest's sake, I studied mechatronics myself, and I thought I was going to build robots right up to the end of third year, maybe. And then I kind of started doing radar, and I really enjoyed it. So mechatronics doesn't really matter. Just follow what's interesting to you. Then finally, something I know absolutely nothing about, well, Othniel can tell you more about that, is more about object recognition. Once you've received all that data back and you've made small peaks of where your targets are, you can do a lot of cool things once the computer gets involved. You do some processing of the data. And you can actually even tell from that picture that with the radar, this is road, those are road markings, trees, pavement on the side. All those things can be, you can kind of figure it out from the radar information and other machine learning algorithms and stuff like that. And you can obviously imagine that this is quite useful for like for a car that needs to be self-driving car that uses radar. You see the road markings there, it knows where it needs to go. So probably more ECE, I imagine. There's a lot of machine learning, neural networks involved. Know nothing about that. This part here is from Othniel's research. I know nothing about this, but basically Othniel is going to try and write a computer algorithm that can detect these little, what they're called whistlers, right? Whistlers, little changes in frequency that has to do with space observation and that kind of stuff. Yeah. What's that? Yeah. Maybe Stacey will drag Othniel into this position as well at some point. So here's my fourth year project. My fourth year project was on synthetic aperture radar. So here's the problem with what I've told you so far. If I send out a signal with a radar and I listen to the signals coming back, I can't really create any sort of image out of that. It gives me no information except distance. All I know, here I've placed 3 targets here, target 1, target 2, target 3. I can tell how far those targets are from that antenna. I can't tell where they are. Target 1 and target 2 are the same distance from my antenna. So on my range response, I get a peak here and a peak here. That peak is from target 1 and target 2. It's kind of useless. What are you going to use that for? You can't tell where a plane is in the sky. You can't hone in on a specific target. You can do nothing with that. The way we fix that is a synthetic aperture. So if I had multiple antennas, for example, you can imagine I can do some triangulation, right? So this target from this antenna is different to the distance from this antenna. And target 2 is, that distance is, well, in this case, probably similar. But you can tell them apart if you had more than one antenna. My project did not make use of multiple antennas, and that's what synthetic aperture is that you move an antenna through space, you know where it's moving to, and you collect information from every position, combine the information together, and it's basically like you have a bunch of antennas. Does that make sense? Yeah? Fairly simple. Radar is actually not the hardest concept if you can get past the maths of it. At the bottom here, this is my actual radar data. You can imagine the antenna is right here at the bottom. The x-axis is amplitude, the y-axis is range. So at a specific distance, I got a few echoes. That's just noise, things to do with the cabling and stuff like that. There's another little peak just a bit further on between 200 and 400. It's probably from the table in front of my antenna. But what I was really looking at is over here between 800 and 1000, which was a little Red Bull can, which was keeping me awake through my fourth year project, which was now empty, but I was able to detect it pretty well. And just to re-emphasize this whole concept is, if my antenna is placed here in the middle, all I know is that that target is that far away from my antenna, which makes a whole little half circle here where my target could be, anywhere in that area. Okay. So what I want to show you next is how this actually worked after doing some signal processing. So again, there's that half circle that you saw in the previous picture. Half circles. There's my radar, there's the antenna, there's my magical little Red Bull can, keep me awake. And as that antenna moves across, you'll see the radar imaging developing at the bottom. So have a look what happens as more information is being collected. And eventually, due to all those radar antenna positions, you can fairly easily see, there's my Red Bull can. This close range imaging using radar, yeah, okay, let's not go into that. But yeah, it's pretty cool stuff once you get some results. Until then, it's really frustrating sometimes. So yeah, I later on had a plastic sheet in front of it, and these radio waves would obviously go right through it, still be able to detect the Red Bull can, put the Red Bull can behind a lot of stuff, still manage to detect it, that kind of stuff. So that's some cool stuff you'd even be able to do in fourth year. Now my master's project, which, to be honest, I don't even understand quite really yet. It's all about solar storms, solar weather. So here we have Earth being absolutely bombarded by solar weather from the sun, which is on that side there. So sorry, yeah, we'll get there. Right at the bottom here of Earth where, so here are all these magnetic fields. These lines here are all the magnetic field lines around our Earth. And what that does is kind of protect us from all this solar radiation coming through. So you can see as this solar radiation hits the Earth, these magnetic field lines respond to it, right? And they like push it away. So right here at the bottom, where all those field lines come together, is Sunai 4, the South African National Arctic Expedition, I think. Something like that. There's Sunai. It's down there by the South Pole, or actually pretty close to the ocean. It's located on this shelf here. And here at the back, you can see a bunch of antennas. And that's a radar. This radar looks kind of to the horizon where these magnetic field lines come into the Earth. And they can they measure the movement of charged particles, plasma, in the air. We read those charged particles, the movement of those charged particles, and then by that we can tell how the solar weather, what's happening in the solar weather, blah, blah, blah. I don't know. But there's Sunai. It's just one of a bunch of stations at the South Pole. It's the only one we have, and it's facing the South Pole over there. This is all part of this super dual auroral radar network, SuperDARN. And all these radars, the data coming from all these radars are collected together. And basically with all this information, we can draw a map of how plasma is moving, and you get a convection map. It looks something like that. So yeah, it's not really, I don't know how much this would mean to you right now, but yeah, this is the movement of the charged particles around this is the South Pole or the North? This is North. You get the same thing for the South Pole. So basically my master's research is in kind of reprogramming this radar, I guess. Just trying to make it better where we can and maybe find some more applications for it, I guess. still fairly new into that. Well, that's the end of my master's, or my overview of radar. I hope that was useful in some way. Even if it is just to kind of excite you, well, get you excited about what's possible out there and how much you'll be able to get done in a pretty short amount of time here at UCT. Oh, 20 minutes. How much did you want? How long did you want me to go on about that? Okay.
A couple of questions if people have them.
Yeah? Do we have some questions? None from you. No, shut up. No? Yeah, okay, sure.
Is there anything fundamentally different between a transmitting antenna and a receiving antenna?
It's an interesting question. So no, an antenna can transmit and receive. The characteristics of the antenna is exactly the same for both. Yeah, they're pretty much the same thing.
It's not a technical question, but can I steal superdon as like a slightly softer non-swear word? Because like somewhere between like don and damn is like superdon.
Yeah, I'm sure they wouldn't mind. They really wouldn't mind. Yeah. Yeah.
Does it work on that principle where they send out a signal that reflects off the target?
Okay, so yeah, with cell phone and telecommunications, you don't really have any, you don't always want reflections, I guess. But that's more about just the one-way direction. So you just want your signal from your phone to get to the tower. When radar, that's, I think, 1 over R2 to the 2 for telecommunications, just one direction. And with radar, you have 1 over R to the 4, where you have it having to travel to the target and travel all the way back. You're looking for a reflection. And just on that, so your cell phone has a really small, low-power transmitter, but the cell phone tower is a really big antenna, a really strong antenna. And the same thing kind of that ties into what Nick just said earlier, was that if your antenna on the other side is big enough and sensitive enough, you can pick up any small signal. So it'll transmit a really high power, which your phone will be able to read then again. So you have another question? Yeah?
Is that repeating the 5G networks, they create bigger?
No, I think it has... Othniel, do you know?
5G it's more complicated than that. There's more software involved.
Yeah. It has to do with bandwidth and that kind of stuff. Less about antennas, I think. Yeah. Yeah.
This is just in general, like for lessons. Do you just like go to the university and be like, I want to do this,
Are you talking about your 4th year project? Or master's?
If you're a master's student,
Yeah.
how do you get to the process of deciding this is what I want to do, this is the person paying for it?
It's a very good question, especially the payment one. That's a tough question. So what I quite like what Stacey's done is open the floor up to all the research groups. She has me down here. She did hers about mechatronics and stuff like that. And it's really great. Gives you guys a view of these things. I think what helps a lot is your 4th year project. So as you go through your degree, you'll kind of decide what you want to do, maybe do some VAC work here and there. You'll get some ideas about things, right? Come 4th year, you'll pick yourself a project. You'll go to a prof. They'll set up a list of projects, or you could go propose your own. And basically, that's when you'll do some actual research into stuff. That's probably, I'd say, focus on getting a good project there, something you're interested in already. And then that step from there to masters is very simple. Prof already knows you. He's already had to supervise you, There's a decent amount of funding in the department. It's pretty rough. It's rough. But if you can find a project that aligns with industry a little bit. So I went with this project because SANSA needed someone to do this. And I thought, well, I'm fairly interested in this. I'll do it. Then they'll fund you.
It's not being the chick from Game of Thrones, like the South African Space Agency.
What's that?
It's not the chick from Game of Thrones.
No, not Sansa from Game of Thrones. The Space Agency.
It's like handing out stats.
But generally, especially if you're a South African citizen, you're likely to get funding. But you just need to be active. Ask around. Get your prof to get you funding.
Theoretically, the NRF.
NRF, yeah. It's pretty much NRF. Any other? Yeah, Imran, you had a question. Oh, okay, shut up. My real name is really long and unnecessary. Yeah. Cool. Anyone else? Are we good? All right. Now for the fun stuff. And this is why you're all here, so you can sit through this. I thought for the rest of the time, because I thought I would be finished a lot earlier than this, I would just go through some examples of the things that Stacey has gone through in class already with you guys. Just some worked examples that you can kind of look at, try yourself, and then look at the answers. So I've also put the answers. In the slides. Let's have a look what we have here. Okay, so I have a few examples on voltage dividers, some examples on Kirchhoff's voltage law and voltage and current laws, and then Thevenin and not Norton equivalent circuits. You guys haven't done Norton, I think. But one Thevenin equivalent circuit example. So you can get out a pen and paper if you're keen. These slides will be available to you, and the answers are all on here. I'm not going to draw anything on the board. Most simple voltage divider over here, right? You have a 20-volt source, you have two resistors, you have ground, and you want to know what the voltage is at point A with respect to ground. Don't know how much Stacey has talked about looking at a voltage with respect to something. But all that means is, knowing what the voltage is at a specific point is kind of useless. You're always measuring it with respect to something. In this case, ground, we just define that point anywhere in the circuit we want. Most of the time it's defined for you, and that's just where we decide 0 volts is. Okay, it doesn't mean that is necessarily connected to the earth or anything like that, but we decide this is 0 volts, and every other point in the circuit is with respect to 0 volts. That 20 volts, what that's saying is that that point is 20 volts higher than this point. That's all that's saying. So when I ask for the voltage at A, I'm asking for the voltage at A with respect to ground. How much higher is A than 0? And in the question, I asked for you to calculate it without calculating current. Just kind of want to push the idea of ratios. That this resistor pair here creates a ratio, and if you go back to the energy idea, you have this very high energy particle here, passes through the resistance, it loses some energy, passes through this resistance, it loses some energy, it loses all its energy back to ground where it has no energy. Okay, so the amount of energy lost there and there is proportional to the resistance of those resistors. Okay, the question let's just show you the answer. Very simple. You're going to say the voltage at A, VA, is just your source voltage. So over your series branch here, and it's just the ratio of how much resistance from ground to your point over the total resistance. So R2 over R1 plus R2 multiplied by your 20 volts gives you 16.67 volts. You're cheated by looking at the next answer. This question here, and what I just want to stretch here is that circuits can look really complicated sometimes. I TA'd the second semester first year course, and one of the profs put a question in there with a bunch of crazy resistors and weird formations, and no joke, 80% of the class couldn't do just adding series resistors together and parallel resistors together. You can always simplify resistor circuits. It's never very complicated. And another thing is that you really need to practice these things. The more you practice them, the easier they get. I can look at this and see a voltage divider immediately. You might not. But the more you do it, the easier it gets. You need to practice these kind of things. So what I see here immediately is there's a series connection. One resistor in line with another resistor. Current only has to flow through both of those resistors. Can combine them. That's 300 plus 800 ohms. Cool? And by the way, if you want to not listen to me and try and work this out in the meantime, go for it. Otherwise, yeah. then you can see that this is a parallel connection. There's two paths for the current to flow. It can flow through that resistor to this line. It can flow through that resistor through this line, to this line. So those two can be added together in parallel, make a new resistance. See that? That series connection there is also in parallel with this one. So once you've added those two together, you can put it in parallel with this resistor. And before you know it, you're really just back to a simple voltage divider like you had here. So there's my new R1, it's just one resistance. My R2, which is those two together, made a new resistance. And R3 I just left behind for a little while, just to show you that that's, again, a parallel connection. Just add those two together. Are we all happy with that kind of concept? Just simplifying circuits down to individual resistors. And then you have a normal voltage divider. And again, you just do your source voltage over the voltage from ground to A. So here's my A. Voltage from ground, or the resistance from ground to A is R4, which is now those two together, over R4 plus R1. Simple voltage divider ratios. Makes sense? And there's the answer. Now, this question I actually really wanted to get to, so I'm glad I got to it. This is the question that you'll come across in your lab soon. So this is really useful to have. Take note of this, make sure you understand it. Remember before I told you that if I ask for voltage at point A, I might ask for the voltage at A with respect to ground. In this case, we're not asking for A with respect to ground, we're asking for voltage at B with respect to A. Okay, it's all the same concept, we're just asking what the difference is between those two voltages. So, back to Stacey's analogy of height, if I say this adapter here is at this height, and this microphone thing is at this height from the table here, I can find out how much that height is. So from ground to this, and then from ground to this, and just subtract the two, then I have the difference between them, isn't it? Simple. So all I'm going to do is I'm going to calculate the voltage at A, I'm going to calculate the voltage at B, find the difference, and that's the voltage between A and B. Cool. Now, here, again, from the previous circuit, you can kind of isolate this side of the circuit. There's a simple voltage divider with two resistors and ground, and you're just looking at a point between those two resistors. Simple voltage divider. You use the same equation. Here, same thing. You have two resistors in series, so you'd add those two together, obviously. And then there's a resistor there, and then again, voltage divider. So the hint I put in here is that VA, I really should say VBA, so it's voltage of B with respect to A, but yeah. VBA is equal to VB minus VA. So start with this equation and just work your way through, because I didn't give you this resistance. And that's what's specific to the lab that you're going to be doing. You don't know what that resistance is, but just put it in your formula. Work it out, simplify it as much as you can, and then you can just plug in any value for R1 that you want into your formula. So calculate VAB, find VB, voltage divider equation, or there, voltage divider equation, VA, voltage divider equation, and just have that R1 as a variable in there. You'll solve for it later. How that looks, something like this. So there, VB minus VA. VB is just 10 times the resistor ratio that we showed earlier, and then minus VA, which is 10 times that resistor ratio. So now, in this case, that's R3 plus R1, so that total resistance there, over the total resistance of the whole thing, which is R3 plus R1 plus R2. Do that, simplify it as much as you want. I didn't simplify it very far, could have simplified it a bit more there. And then solve for VAB. Something you're going to have to get very comfortable with very soon, which in my experience some first years do struggle with, is this, 8 kilo ohm. You need to be able to, when you see 8 kilo ohm, you should know it's 8 times 10 to the power 3. That's usually the way we write it. So there, 8 times 10 to the power of 3, that's 8 kilo ohms. You need to see that pretty quickly. You need to know mega ohms times 10 to the power of 6. It's all in your lab manual. But being able to, because it's a very quick mistake to make, and your answers are out by a factor of 1,000. You don't want that. So we found a negative sign for VAB, which is negative 1.58 volts for R1 equal to 0. Negative voltages are fine. There's nothing wrong with a negative voltage. Negative currents are complicated, a bit more complicated. But negative voltage is okay. Just what negative voltage means, it just means that the voltage at B was lower than the voltage at A. That can happen. If I define this to be 0, I can have negative voltages. If I put a battery here that sends the voltage lower, I have a negative voltage. It's all just with respect to 0. It doesn't mean anything by itself. So negative voltage just means VB was lower than VA, voltage of B with respect to A. So that's fine. Kirchhoff's voltage law. So here I have a circuit that's very easy to solve without Kirchhoff's voltage law. I wanted to keep it as simple as I possibly can. One way to solve the circuit is just to find the total EMF in the loop. So that's 2 and 5. Total resistance in the loop, 1 kilo plus 1.5 kilos. And then you can just solve for current with Ohm's law. So that's one way to do it. It's fairly simple. But I specifically asked you to use Kirchhoff's voltage law. So to solve for the loop itself. Just check. Cool. So I defined this point to be ground. Sometimes you'll find it defined already. Sometimes you'll define it yourself. So for the rest of the circuit, everything is with respect to 0 volts. This battery here, or the source, just means that the point above it is 2 volts higher than below. If this was if this is 0 volts, which we've defined it as, then that point there is 2 volts. We don't know what the voltage at either side of this is because we don't have a defined voltage on this branch. We don't have a defined voltage on that branch. There's resistors that will drop voltages. Drop or increase voltages. You never know. It depends on the current. So you really can't say what the voltage is here and the voltage is there. All you know is that this side is 5 more than this side. Does that make sense? Okay. So the only defined voltage we have in the circuit is ground, which is 0. And we can tell that just by knowing that this is plus 2. So this is where it gets a bit rough. So bam. So the steps, I kind of tried to work out a few steps for you to follow to make this as easy as possible. And it kind of goes like this. First, choose a direction for your current in every loop and in every branch in your circuit. So as complex as the circuit might be, just decide where your current is flowing first. Take an educated guess. I made an uneducated guess, as you'll see now. I said the current is flowing this direction, when in fact that's a higher voltage, so it'll probably push in this direction and charge this battery. But the idea is that you define your currents. Now, I like to define my currents on the circuit itself, so on the line. So I'm saying that my current is flowing clockwise through here. And once I've defined my current directions, I can define what my resistors will do because of that current. Okay, so that's why you have to do the current first. You can decide everywhere in your circuit which direction currents go. After you've done that, defined your currents, you define your voltages. Now, sources are simple. They're always, this is a 2 volt source. That point will always be 2 volts more. So you always have, I draw arrows pointing towards the higher voltage. It's pretty common to do so. You'll see that in a lot of textbooks. So my arrow now off the circuit, not current, current's on the circuit, is saying that this is 2 volts going in that direction, where that's higher and this is lower. If current is flowing this way through this resistor, right? That means that, remember, resistors use up energy, so your voltage is dropping, going to a lower voltage on this side. So my arrow is pointing to the higher voltage would be this side of the resistor, if the current's flowing that way through the resistor. And I've written down what that voltage would be. So with respect, I don't know what I1 is, but knowing what I1 is, it's just multiplied by the resistance, right? V equals IR. IR. So the voltage across that resistor is equal to that, and I know that the higher potential will be this side based on the direction I picked for my current. Keep going around the loop. There's a source, pretty standard, 5 volts. That's got to be 5 volts higher than this. Just draw your arrow to the higher voltage. And then for the large resistor here, current coming through here, so it will drop in the direction of the current. So as the current flows through this resistor in this direction, this is the lower voltage. My arrow points towards the higher voltage, and that voltage is equal to I1 times the resistance. Does that make sense to you all? That's fairly, once you get that, you can solve the most complex circuits, I promise. If you don't make uneducated guesses like I did here. Turns out, so you write down your KVL, Kirchhoff's voltage law, you say the sum of all the voltages in the loop is equal to 0, right? So I'll just start at the point I know. I mean, you can start anywhere really, but I started here. And I'm saying I'm increasing by 2 volts, so plus 2. As I'm going, this is a decrease in voltage, so minus. Minus that voltage to go from that point to there. Minus 5 volts. See the arrow is pointing against the direction I'm going in, so it's minus another 5 volts. And then when I get here, I'm minus another voltage, which is dependent on current. Back to my point where I started. Just go in a circle and sum all your voltages together. When you sum all those voltages together, they have to equal to 0. Okay, that makes sense. We got back to the point we defined as 0. It has to be 0. So solve for I, and you get a negative current. Now that's the issue. I told you negative voltages are fine. Negative currents mean you made a mistake. And that mistake is that you just chose your current to be in the wrong direction. Your value is fine. The value will work out. The negative sign only means that current was actually flowing in the different direction. So, tedious, but it will make sure it will help you not to make mistakes. Here you have the circuit with the current in the correct direction. I labeled it I2. And I2 is positive value, going in the anti-clockwise direction. You can solve for that again. You'll just get the same answer. You'll get I2 equal to 1.2 milliamps. But from this point on, and this is kind of also a concept you really need to be comfortable with, now that I know the current, I can calculate whatever voltage I want in the circuit. Start by the point you know. Start at 0. To find the voltage at A with respect to ground, we start at 0, we go up 2 volts, and now we have that. We have I2. So we can just solve for that voltage across there. We're going up in voltage. So then you find, so following the green path here, we'll say 0 plus the 2 volts plus that voltage because we're going up that resistor. The current is coming in the opposite direction, so we're increasing in voltage. And you get that answer. Could also go through the other way. From ground, that's a drop in voltage. See how arrow's pointing this way? So minus that. So now we have a negative voltage with respect to ground. And then up 5 again. And we get back to the same answer, 3.2 volts. Practice these things, you get very good at them. And then exams for your electrical engineering comes fairly simple. Yeah. Sure.
So say in, like say, the previous one.
Mm-hmm.
So in that I said, in the current flow opposite the direction of the conventional current.
Of conventional current.
Yes, like say for instance, you said that the current flowing through from the 5 volts positive side terminal. So I mean on the 2 volt source.
Yeah.
Does that mean the current flowing from the positive side?
Current can flow either way. Can flow through a resistor. It will charge your battery. Yeah. All right. Get the message. Time's up. Oh, you guys are cheating me. Cheating me out of 2 minutes. Shocking. There's some more examples in here. You can go through it yourself.
We don't go early to computer science. You don't get a seat.